Hello, welcome to the photoelectric effect. I'm hoping that you have seen my analogy video of this before doing this one. There are three formulas found on your formula sheet. And so what we've got here, this is your kinetic energy of your electron. This is the energy of the photon. And this is the work function, or the phi. Now, the amount of energy that the electron has coming off the surface is equal to the amount of energy that we've got coming in minus the amount of phi that the surface is giving to this called the work function. Now, if we want to find out how much energy that electron actually has, we measure it by stopping that electron by providing a potential difference against the motion of the electron. And that's what this formula is asking us for. The work function can be found with the minimum amount of energy required to give, and that's where this F naught is. This is what we call the threshold frequency. The minimum frequency needed to cover the phi, or the work function, in order for us to see electrons actually be produced. So if we take a look at the money analogy again, this is just energy in, right, which is HF, that's radiation. The emitted electron is energy out. So that is kinetic. And the work function of that is your flat in this entire conversion. So let's take a look at a couple of examples before you try one. Okay, the first one here, the energy of a photon with the wavelength of 5.20 times 10 to the 2 nanometers. That translates to 5.2 times 10 to the negative 7 meters. Now, because we have this in wavelength, instead of using HF, we're going to use HC over lambda. We've done this before. But if you wanted this in electron volts, you're going to use 4.14 times 10 to the negative 15 electron volt seconds. That's also on your formula sheet. You don't need to memorize it. For H, for Planck's constant. We've got 3 times 10 to the 8 as the speed of light. Divide that by the 5.20 times 10 to the negative 7 meters. And when you calculate all that out, you should wind up with 2.4 electron volts of energy. Here we're asked to find the stopping voltage given a certain amount of energy in joules. So E is equal to QV, again, 2.17 times 10 to the negative 18 joules of energy. The charge on that electron is 1.6 times 10 to the negative 19 joules, multiplied by the voltage, which, when you divide this out, you wind up with a potential difference needed of 13.6 volts. So, give this next one a try. 1.8 electron volts. What is the stopping voltage? Okay, so you should have wound up with an answer of 1.8 volts when you tried this. Now, a lot of students will take the 1.8 electron volts, convert that into joules, so that they can take that energy and divide that by the 1.6 times 10 to the negative 19 coulombs, the charge on an electron, multiplied by the voltage, and you still wind up with 1.8 volts. If you realize that, well, 1.8 electron volts is an energy, but the charge is on one electron is 1 electron worth, multiplied by the voltage, then 1.8 volts. In fact, this is how they measure the energy and why electron volts are so used. The stopping voltage is the amount of energy in electron volts. Try these three questions in your textbook. Make sure you're matching up before continuing on. If you got questions, let me know. One more example before we continue on. If the work function is 1.8 electron volts, so the surface is charging a fee of 1.85 electron volts of energy. So if you think about it, the energy coming in, this HF, has to equal the fee coming in, right? So the energy coming off of this is 0. All this just goes to pay the fee, which is why we use HF naught. We know the work function is 1.85 electron volts. For H, we're going to again use 4.14 times 10 to the negative 15 electron volt seconds because we've got energy in electron volts. And finding that threshold frequency, when you divide it out, you wind up with 4.47 times 10 to the 14 hertz. That is your threshold frequency. However, if you wanted to figure out the wavelength of this, you can easily convert that using the universal wave equation. And if you did, you would find that 6.71 times 10 to the negative 7 meters, or red light. So pause the video. Give this next one a try where you're trying to find out the work function, but this time you've been given a work function in joules. So I don't know if you also figured out the wavelength to find this to be UV light. However, it's just that work function in joules. We're going to use Planck's constant, but we're going to use the 6.63 times 10 to the negative 34 joule seconds because you've got your energy, your work function in joules, and the answer is 4.75 times 10 to the 15 hertz. Next example here. Oh, before you do that, please complete 718 numbers 1 to 2. Give those a try before continuing on with this video. Okay, next question. Here we've been given the energy of the electrons. We've been given a wavelength of the blue light shining on the surface, and we're looking for the threshold frequency of that metal. So the formula we're going to probably be looking at on our formula sheet is this one. Oh, that should be minus W. EK of the electrons, well, that's easy, that's in joules. But instead of HF, we're going to change that to HC over wavelength because we've been given the wavelength. And instead of the work function, we're just going to use this with the threshold frequency in order to solve. Now, to simplify this, we've got 2.6 times 10 to the negative 19. HC divided by wavelength actually gets you 4.9725 times 10 to the negative 19 minus, and we're going to use 6.63 times 10 to the negative 34 joules times frequency. You're going to need to subtract this first, which means you got 2.3 times 10 to the negative 19 is equal to, which is going to put HFs because I'm running out of space. Dividing both sides by H, you'll get 3.58 times 10 to the 14 hertz as being your threshold frequency. Last example here. In this case, aluminum has a work function of 4.08 electron volts. We've got energy coming in the form of radiation and an electron coming out. This is what we want to find the speed of. We've been given this work function, so we can find out how much energy this electron has by taking how much energy is coming in minus the work function, minus the charge here. So instead of 8, we'll use hc over lambda again. Now, given the 1.25 times 10 to the negative 9 as your wavelength, h as being a Planck's constant, we're going to do the 4.14 times 10 to the negative 15 because it's in electron volts, and we can find this in electron volts, multiplied by 3 times 10 to the 8, all divided by 125 times 10 to the negative 9. So this has 9.94 electron volts coming in. So if you got 9.94 coming in, you're charging a flat fee of 4.08. How much you got coming out? Well, that's going to be 5.86 electron volts coming out. If we convert that into joules per electron volt, the amount of joules that means is 9.37 times 10 to the negative 19 joules. And that is what we're going to use equals 1/2 mv squared, making sure we're using the mass of the electron. You should wind up with a velocity of 1.43 times 10 to the 6 meters per second. Okay. Again, if you're having any difficulties, you're typing along, not getting the same answers, please let me know. And next step is to complete these 3 questions from the textbook before moving and trying on the homework assignment. If you got any questions, again, let me know. Thanks for watching.